July 1st, 25. Astronomers spot a giant comet hurtling into our solar system at 130,000 miles per hour. At first, 3E/Atlas looks like any cosmic wanderer, but its orbit is pure hyperbole, an eccentricity of nearly 6, confirming interstellar origins. Then the real shock hits. At 6 times the Earth, sun distance, far beyond where water ice can thaw, this object erupts with jets, and JWST shows its coma is 99% carbon dioxide, almost no water at all. The rules of comet chemistry are upside down. Is this the opening chapter of a cosmic riddle science is racing to solve? When the Atlas Survey Telescope in Chile flagged a new object on July 1st, 2025, the initial data set off a rapid chain of calculations. This wasn't just another icy wanderer from the Oort cloud. Its orbital eccentricity, nearly 6, stood out immediately. Most comets trace elongated loops, bound by the sun's gravity. Not this one. With an eccentricity so far above 1, its path is hyperbolic, meaning it's not coming back. It's a visitor from beyond, making a single pass through our solar system before heading back into interstellar space. The object quickly received its formal designation, 3I/Atlas. The 3I marks it as only the third confirmed interstellar object, following Oumuamua, and 2I/Borisov. But there's a key difference. Early photometry suggested a nucleus up to 15 kilometers across, making 3I/Atlas not just an outlier in trajectory, but in sheer size. That's hundreds of times the surface area of Borisov, and orders of magnitude larger than Oumuamua, which was closer to a city block than a country. Even the lower bound estimates, based on Hubble's upper limits and the object's reflectivity, put it in the multi-kilometer class. The scale matters. A nucleus this large carries more thermal inertia, meaning it should be slower to react to sunlight and less prone to sudden outbursts. Yet, its brightness and coma size don't fit the standard comet template. The surface area calculations, factoring in the observed magnitude and assumed albedo, imply a body with enough real estate to host entire towns, all wrapped in a cloud of gas and dust that stretches tens of thousands of kilometers across. Compared to its predecessors, 3I/Atlas is in a league of its own. Oumuamua was a tumbling sliver, Borisov a more conventional comet, but still modest in scale. This new arrival is a heavyweight, barreling through on a path that doesn't curve back. Its mass and momentum are reminders. Most interstellar objects passing through the solar system are too small or faint to ever be noticed. For one this big to appear and to be moving so fast is statistically extraordinary. That's why astronomers are watching closely. When a country-sized chunk of ancient ice and rock from another star system flies by, every detail becomes a clue to what's possible beyond our sun. Out past Jupiter's orbit, where sunlight is little more than a distant glow, 3I/Atlas began to stir. Astronomers tracking its path expected silence. At 6.4 astronomical units from the sun, the temperatures hover far below what's needed to wake a typical comet. Water ice, the usual culprit behind a comet's coma, stays frozen solid until about 3 astronomical units. Yet, telescopes recorded a bright, expanding shroud of gas and dust enveloping the nucleus, a clear sign of active outgassing. The scale of this activity caught scientists off guard. Calculations based on the coma's brightness and the estimated size of the nucleus, up to 15 kilometers across, showed that more than 1/5 of the surface was already venting material into space. That's a level of activity rarely seen, even among the most hyperactive comets in our solar system, and almost unheard of at such a distance. For comparison, most comets only manage a few % of their surface actively jetting, and only when they're much closer to the sun. This early and intense outpouring defied standard comet physics. The energy from the sun at 6.4 astronomical units is simply too weak to account for such robust outgassing if water ice were the main driver. The numbers didn't add up. Something else, some other volatile or a structural quirk, had to be fueling these premature jets. Monitoring teams began scrutinizing every data point, searching for clues in the evolving coma as the object continued to break every rule in the comet playbook. The normal boundaries of the so-called water-ice line seem meaningless here, leaving astronomers with a puzzle that pointed well beyond familiar thermodynamics. The James Webb Space Telescope turned its attention to 3I/Atlas just as the comet's activity was raising eyebrows. Spectra from JWST's NIR spec instrument delivered a result that upended every expectation. The coma is almost entirely carbon dioxide. The numbers are stark. Carbon dioxide outgassing measured at 129 kilograms per second, while water vapor barely registered at 6.6 kilograms per second. That puts the carbon dioxide to water ratio at 8:1, a value that stands 6 sigma above the trend for any long period or Jupiter family comet. In percentage terms, nearly 90% of the detected gas is carbon dioxide, with water making up less than 10%. Even among the handful of solar system comets known for high carbon dioxide, none come close to this profile. JWST's spectra also revealed a coma rich in tholins, complex organic molecules that give the dust cloud a deep reddish hue. Tholins form when organic ices are exposed to ultraviolet radiation over millions of years, hinting at a surface that's been weathered by interstellar travel. The signature appears as a broad absorption in the near-infrared, a fingerprint of prolonged UV processing not seen in most solar system comets. The science team behind the JWST campaign, led by Michael S. P. Kelly and collaborators, confirmed these findings with repeated observations. Each pass yielded the same inverted chemistry. Carbon dioxide dominates. Water is a trace. Carbon monoxide and carbonyl sulfide appear in small amounts, but nothing approaches the runaway carbon dioxide production. The spectral lines are unambiguous. This is not a comet that fits the standard mold. Instead, 3I/Atlas is showing a molecular fingerprint that has never been cataloged before, and it's forcing comet researchers to rethink what's possible when a visitor comes from far outside the sun's chemical domain. Carbon dioxide dominates the story of 3/Atlas, not just in chemistry, but in the physics that drives its behavior. Most comets wait until they are close to the sun, inside about 3 astronomical units, before sunlight can rouse their water ice into action. But 3I/Atlas started venting gas far beyond that, out past Jupiter's orbit, where temperatures are too low for water to sublimate. The answer lies in the volatile nature of carbon dioxide. Unlike water, carbon dioxide ice can turn to gas at temperatures as low as 20 to 30 Kelvin, which means even the faint warmth of sunlight at 6 astronomical units is enough to set it free. The nucleus, estimated at up to 15 kilometers across, is not a solid block of ice. Instead, models suggest a porous structure riddled with carbon dioxide-rich pockets, something like a cosmic Swiss cheese. As sunlight seeps in, carbon dioxide trapped in these voids begins to sublimate. Gas pressure builds up in the confined spaces beneath the surface, eventually forcing its way out through narrow vents or weak spots. These jets can erupt with surprising force, carrying dust and even large ice grains with them, and explaining the early, robust coma seen in telescope data. The pressure inside these pockets depends on the size of the pores and the thermal conductivity of the surrounding material. In some regions, just a small temperature increase can trigger a sudden release, sending jets of carbon dioxide gas into space at hundreds of meters per second. Thermal models of comets like 67P/Churyumov-Gerasimenko have shown that even a modest gradient in porosity can funnel gas toward the surface, concentrating activity in patches. For 3I/Atlas, more than 20% of the surface appears to be actively venting, an unusually high fraction for a comet of this scale. The energy required to sustain this is supplied by sunlight, but the efficiency comes from the structure, high porosity, low thermal inertia, and a distribution of carbon dioxide ice close to the surface. The result is a body that can erupt with activity long before water ice gets involved. The chemistry points to an origin outside the familiar territory of our solar system. Thick disk stars, older and poorer in heavy elements, shape their protoplanetary disks differently. In these metal-poor, oxygen-starved environments, the carbon dioxide snowline sits farther out, and the balance of ices shifts. Instead of water-rich bodies like those that formed here, a comet born in the thick disk could be loaded with carbon dioxide and other hypervolatiles. The unusually high carbon dioxide to water ratio in 3/Atlas's coma, paired with hints of isotopic differences, supports the idea that it condensed from a disk with a very different chemical recipe, one that left it primed to break every rule in the comet playbook. Avi Loeb, the Harvard astrophysicist known for championing bold possibilities, has called 3I/Atlas the most promising test case yet for the alien artifact hypothesis. He points to the comet's nearly retrograde orbit, 175 degrees, slicing through the solar system on a path only 5 degrees off the ecliptic. That trajectory is rare enough to raise eyebrows among orbital dynamicists. But Loeb's real focus is the timing and the chemistry. He notes that 3I/Atlas will reach Perihelion, its closest approach to the Sun, on October 29, 2025, right as it swings behind the Sun from Earth's perspective. For Loeb, this geometry feels almost too perfect, as if the object is designed to pass through the planetary plane, visiting Mars and even skimming near Jupiter before vanishing back into interstellar darkness. The argument isn't just about orbits. Loeb and his colleagues highlight the comet's photometric wiggles, the absence of a classic water ice surge, and, most provocatively, the inverted chemistry. They ask, if this visitor is natural, why doesn't it behave like any other comet we know? Why does its coma remain almost pure carbon dioxide, with water vapor barely detectable? In Loeb's view, the anomaly invites extraordinary explanations. Could 3I/Atlas be a disguised probe? Its carbon dioxide jets a clever cover for something artificial? Or is it a natural body from a star system where planetary chemistry runs in reverse? As 3I/Atlas swings through Perihelion, every telescope on Earth and in orbit will be watching for a water surge. If the comet's water production suddenly spikes, standard models win and the mystery shrinks. If water stays low, if the coma remains dominated by carbon dioxide even at peak solar heating, then the anomaly stands, and the case for something truly new or truly strange grows stronger. The countdown to October 29th has begun. Until then, 3I/Atlas stands as direct evidence that our solar system is not the standard, and that cosmic diversity is greater than once believed.